All right, this is our seventh set of notes on the graphical representation of VLE. So in this set of notes, we'll introduce the concept of volatility, relative volatility, and then we'll end with talking about phase behavior at high pressures. And by phase behavior, I mean vapor-liquid phase behavior. Okay. So we've talked about PXYs and TXYs, and they've been motivated by, talking about distillation and vapor-liquid equilibrium state separation, so vapor-liquid separation processes. And in a vapor-liquid separation process, my goal is to take, say, a liquid, heat it up to my two-phase region, and then to concentrate my most volatile component in that vapor phase. So I'm going to pull a distillate out of my, say, flash drum, for which Y is greater than Z is greater than X, right? It has a greater concentration of my most volatile component than the mixture I started with. When we looked at TXYs, we said, well, pressure is fixed. My most volatile components could be the one that's easier to boil. It's going to be the one with the lower pure component saturation temperature. In a PXY, where temperature is fixed, we kind of assess the volatility of those two components based on their pure component saturation pressures. The more volatile component is going to be the one with the greater Psat at a given T. Okay. So here we introduce volatility. Okay, and how we define volatility is mole fraction of vapor relative to mole fraction in liquid. Okay, so if I think about my TXY phase diagram, I heat my system up to the two-phase region, draw my isotherm, I find my Y in equilibrium with the X. Okay, so that Y relative to that X would give me the volatility of my component I at that temperature and pressure in this case. Okay, and the greater the value of K, the greater the volatility of that component, right? And so the fatter my phase diagram, the greater the volatility of component I. Okay. So relative volatility, so if we want to try and separate two components based on their volatilities, okay, relative volatility is going to be the relevant quantity. Okay, so the idea would be is if I take the ratio of the volatility of component 1 relative to component 2, that gives me alpha, my relative volatility, and so that's going to give me, or allow me to compare the volatility of one species relative to the other. So if component 1 is more volatile than component 2, then alpha is going to be greater than 1. Okay? And when we talk about separating two components based on the relative volatility, the idea being the larger the value of alpha, the greatest the value of alpha, right, the easier it is to separate those two components. Right? So the greater the value of alpha, the easier it is to separate those two components because their volatilities are going to differ by a large amount. Okay? And the limit that alpha is 1, then we just have an azeotropic system and no separation is going to be possible. Right? So relative volatility is incredibly important. And so if you were to look in a handbook, so for instance, Henry Keister has a handbook about, related to designing distillation columns, and I recall a table in one of his introductory chapters in which he has a list of some known columns that presumably he's designed, and then what he has in the column next to it is number of stages, kind of giving you a measure of the difficulty of that separation, and the relative volatility of the two components that you're separating. Okay? And in general, right, the number of trays required to achieve a given separation scales with the relative volatility of your two components. Right? And these things kind of come out too when we talk about things like the Underwood correlation and such at total reflux, where we're essentially scaling alpha with the minimum number of stages required. All right? So alpha is an incredibly important quantity. And just knowing alpha can give you a sense or an idea of what it's going to take to separate those two components via vapor-liquid separation, right? Via distillation. All right, and so if, one last thing before the next slide. So K is equal to, so Ki would be Y over Xi, Kj, Yj over Xj. And if this were a binary system, those mole fractions have to sum to 1. All right, so Xj would be 1 minus Xi, and so if I just plug in mole fractions and rearrange, right, I can actually solve for an expression for Y in terms of alpha and X. Okay, And so, what that's just going to come down to is, if I were to plot on a McCabe-Thiele diagram y versus x, all right, then I solve for y in terms of x and alpha. So if I just look at different values of alpha to see what that looks like on a McCabe-Thiele diagram, right, what I find is as I increase alpha, right, the distance between my curve and my y equals x line increases. Right? And so we said alpha is a measure of the ease of separation, idea being as alpha increases, the separation becomes easier. Right? And what I mean by that is if I had some feed, so let's say, I have a, so if I have an x composition of 0.4, okay, and if I have relative volatility, this could be pretty close to 1 on this red line, right? And I read across to the left, I'd find my y, which is going to be pretty close to 4. In theory, it should be a little greater than 4. Now I go up to my green line, given by this system with a larger relative volatility. My y value in equilibrium with the x is increasing. And as I continue to increase alpha, the value of that y in equilibrium with that same x is increasing. So at this highest case, if I have a liquid phase of 0.4 mole fractions, right, my vapor looks like it's greater than 0.8. So the larger the value of alpha, the greater the value of y relative to x, right? So the easier it is to separate it. So if I'm thinking about distillation in your separation class, the least number of stages it would require to hit desired purity. Or if I'm thinking about a flash drum, if I take that mixture, send it to a single stage unit, the greater the value of alpha, the greater the y I'm going to get coming out the top of my drum. Okay? And where this comment was on the last slide that I just skipped through is, later on we'll talk about Rayleigh law or just phase equilibrium criteria in general, and we'll be able to come back full circle and we'll be able to write down expressions for volatility and relative volatility in that context, right? And for example, if I had a system that obeyed Rayleigh's law, I could define define these quantities just in terms of vapor pressures. But we'll come back to that later on. Okay, and if anything, it'll just further confirm that I can use vapor pressure at a given T as a measure of how volatile a component is. Right, and so if I compare two pure component vapor pressures, I can get to the same sort of results. The last real short set of a couple points we'll make is VLE and elevated pressures and temperatures. And so what I mean by that is when we've looked at kind of these TXY phase diagrams so far, plotted with respect to the most volatile component, they've always been at, so if I think about a TXY, pressures of around 1 atm. Right? Why pressures of 1 atm? Well, those are pressures that we're typically going to operate at in a given distillation process. So what I mean by here, by VLE at elevated temperatures and pressures, is what happens when we increase the pressure all the way to the point where I exceed the critical point of that least volatile component. Okay. And so here I have PXY. So this is ethanol water. Okay, so it's plotted with respect to ethanol, the most volatile component. And so down here I'm at 200 degrees C. Okay, and my TXY phase diagram spans the entire composition region. Okay, and what's labeled here as a reference is if these are all at different temperatures, critical temperature of ethanol is 240.77 degrees C, water is 373. Okay, and so what happens is if I take this system and now I look at a higher temperature, so now I'm at a temperature of 250 degrees C, which exceeds the critical point of ethanol. Okay, if you were to zoom in, what you would find is my TXY phase diagram now no longer goes to the pure ethanol limit. All right, it actually falls short. My dew line pinches my bubble line before I get to that point. And as I continue to increase the temperature beyond the critical temperature of ethanol, my most volatile component, right, my TXY phase diagram continues to retreat, and I get further and further to the right. Okay, this happens all the way. So this is at 350. If I were to heat this all the way up to the critical temperature of water, then my TXY phase diagram would completely disappear. Right? So as I heat this system up, this mixture up beyond the critical temperature of my most volatile component, I'm going to get further and further to the right. Right? And so what's going to happen is the mole fraction that I can have, mole fraction of ethanol that I can have in this mixture with water is going to become less and less to keep me at subcritical mixture temperature, right? So you can kind of think, the critical temperature of my mixture is going to lie somewhere between ethanol and water. Okay, the pure water limit is where I'm going to have that highest critical temperature. So as I increase my temperature, the amount of ethanol that's going to be found in that mixture, in that subcritical mixture, is going to become less and less, right? And I get further and further to the left in my plot. Okay, so that's TXY at elevated temperatures and pressures. And if I were to look at it on a McCabe-Thiele diagram, right, I get the same result. You get 200 degrees C, it goes the entire way. This is an example of an azeotropic system, a minimum boiling azeotropic. So actually pinch the azeotrope and go a little, or hit my y equals x line and go a little below up here. But then as temperature continues to increase, my loci is going to continue to retreat. Okay, you could do a similar exercise with a TXY, but it's one and the same. Okay, and that wraps up that last set of notes.